Hello, everyone. So today we're going to continue with our introduction to formal groups that we're going to use later on to study the points on an elliptic curve over p-adics, over local fields. But in our case, we're going to be interested like what happens, in particularly over QP. I just wanted to. I had an interesting discussion with one of the students after class last time, and it's just that introduction to formal groups. The very first time you see it, it's quite. You have to see this a few times to really understand what's happening. So just to recap, what happened last time was that we changed coordinates, and in changing coordinates, we realized that we are able to write formal expansions. By formal, I mean power series expansions. And by formal, we mean that we don't care about a priori about the convergence. It's just power series expansions for points on the elliptic curve that later, when we switch to a complete field or a complete ring, then we can evaluate there and actually get points over those completions. But what happened is that we have points. So this is, first of all, in the coordinates in x, y, I want to add p and q. And what happened is that, well, I can change variables. So here is, I have my xy coordinate plane and then my zw plane. And what I did was give coordinates for points on the zw plane. But first of all, we realized that w is actually, we can write it as a function of z if we allow for these infinite expansions, these power series. So formally, I can write it as a power series in z. So actually, I only need to know what's the z value. So if for p there is a z1 that corresponds to that, it corresponds to a z1. So it really is z1 w1, but we only care about the z value because the w comes for free from the z value. And if we, in the change of variables, q corresponds to this point here, and it corresponds to a coordinate z2, then the point r is going to be the third point of intersection. If you do the lines go to lines in this change of variables. So it goes here, and I get a third point of intersection. That's a third z value. And then the addition, what it does is like I reflect, or I do the line that goes through O. This line, remember, vertical lines go through O. And what I did is, well, then P plus Q is over here. So if you reflect with respect to O, do the line through O, then I'm going to find here what I'm going to call Z1 plus addition on E, Z2. Okay, and that is what we're after. We're after doing addition formally on these z values, which eventually are going to be elements of the maximal ideal of a complete ring. And that's precisely what we were after. Like, can we write a formula for that addition so that I can put a structure, a group structure on the maximal ideal of a local ring and just do addition directly on the local ring? And that's exactly what we did. We did this whole process last time, and what we did was start with an elliptic curve in our regular Weierstrass form, and then change variables to the ZW plane, recursively solve this equation. And by recursively, what we did was Hansel's lemma gives you that recursive solution, and that gave me a way to write W in terms of Z. Okay, so here, this is the expression of W as a power series in Z, and then going back to the font in black. So going back to the X and Y coordinates, then I can rewrite the X coordinate again as a power series in Z, and I get an expression, and then I get an expression for Y, and like an expression for holomorphic differential, which we'll come back today. And then we get an expression for the addition of two z values, which was what I was after. And that gives me some power series now in two variables. This is the beginning of the power series. It starts like that, z1 plus z2 plus terms of higher order. And what we said is like, well, this addition, formal addition as a power series, it actually comes from the addition on the elliptic curve. So it inherits the nice properties from that addition. It's commutative, it's associative, there are additive inverses, and 0 is the neutral element here. Because remember that our change of variables switched O corresponds to the value z equals 0, right? It goes to in this change of variables, O is at 0, 0, so the z value is 0. Okay, so our O is 0 there in the maximal ideal, and it has all these properties. So as mathematicians do, now take this and formalize it and just talk about it in abstract terms and see how much mileage we can get out of it. There is other situations where this comes up. For example, at UConn with the graduate students, we're doing a reading course on local class field theory, and formal groups are a big part of that in the Lubin-Tate theory, for example. So there's other situations where formal groups come up and are very useful in applications in number theory, I guess. All right, so here is what we did at the end of the last class. Here's the definition of a formal group. So a formal group, a one parameter commutative formal group, is a power series. So it's just an addition law without really any points. I'm just giving you how to add in the abstract without the actual points that are part of the group. Later we'll put group elements with this addition on top. So it's a power series. It has to start with x plus y plus terms of higher order. So it looks like an addition. It is associative. Remember that we said, like, if you think of like this capital F as a sum, then you can also write this. So if you write f of x, y, or if you define for notational purposes x plus y with that plus over f to be f of x, y, then this property just reads x plus in f of y plus z equals x plus y plus z, which is just the usual associativity. So if you, this is a very cumbersome notation when you use it as a power series in two variables, but if you sort of think about it, just f is just, capital F is just addition, then it makes sense that this is just associative. This is the associativity. It is commutative. We assume that there are inverses, so there is some other power series that for every t, the power series evaluated at t, that is the additive inverse of it. So when we add them together, you get 0, and that 0 acts as a neutral element. And that's, by the way, that you can see here, that if you plug in 0 there, all the other terms are actually mixed terms, and then it's just going to vanish, and you just get x. Okay, so, and then we call F the formal group law, and as I said at the end of the class, always, it turns out that these conditions, there's a lot of redundancy, and parts A and B are actually the core of the definition, and you can show that A and B imply in this formal setting D plus E, and in fact, if R has no torsional potent elements, then A plus B implies the other conditions. All right, so what else do we need? Again, like mathematicians do, once you have an object, then we also want maps between those objects. So let's define what is a homomorphism of formal groups. So homomorphism So let's start with two formal groups. So let F and G be formal groups over a common ring R. Then homomorphism F from one to the other is a power series. So F is simply a power series in R with coefficients in R, such that F of capital F equals G of f of x, f of y. Again, if you think in our alternative notation, all this says is that f of x plus y added in the formal group F is the same that f of x plus f of y added in the formal group G. Okay, this looks almost like an X, so let me change it. There you go. So that's typically how we define homomorphisms, that a map that respects the addition laws. And then we say that two formal groups are isomorphic. And GR isomorphic if there are homs F from F to G and G from G to F, such that well, they're inverses of each other. So what you need for that is that f of G of t equals G of f of t equals t is the identity map. Okay, so let's start with some examples of all this that are not just the one for the elliptic curves. So for example, we have what's called the formal additive group. The formal additive group is called GA, so it's G hat A. This is a convoluted notation, but so the A is for additive, and the little hat, we actually use often this hat to denote something that is a formal group. I need to give you, so the name for it is just pretty much irrelevant. It's just a name. What I need to give you is what's the power series. With the power series that is addition in this case is just x plus y. Okay, so it's not a power series at all. It's just a polynomial. And it turns out that that polynomial has all the properties that you need. It's definitely commutative. That's just addition, so it's associative. The inverse is just minus x. For x is minus x, gives you 0, and 0, x plus 0 is equals x. So it all works. Okay. Another example is the formal multiplicative group. This one we call GM, and the formal multiplicative group is x plus y plus xy. Okay, why is that? That's because remember how you can write units in rings with a maximal ideal m. You can write them as 1 plus m, 1 plus something in there, So this is, what is this? This is 1 plus x times 1 plus y minus 1. Right? Yeah. So it's meant to be sort of like a multiplication of units, thinking of units in a local ring. Okay. Then the formal group we are interested in, for our purposes, we want an elliptic curve defined over a ring R, and then the formal group attached to the elliptic curve is going to be the one with f of z1, z2, the addition law we defined before. Okay, that law satisfied all the properties that we had, and so it's sort of like we use it as our prototype. How about what I have in this slide? How about homomorphisms? Some examples of homomorphisms. Well, I have, for example, if I have a formal group, there is always the natural homomorphisms, which are multiplication by M maps. So I can multiply by M. How? Well, I do have an addition defined inductively by, I want, well, 0, the map 0 of T is just the 0 homomorphism. And then the multiplication by M plus 1, so this is for integers. Multiplication by M plus 1 is just going to be addition of whatever multiplication by M is and add T also. And if you want to do the negatives, multiplication by M minus 1 is going to be multiplication by M and the inverse, whatever the inverse map is for that. Okay. Okay. So, by the way, it is a good exercise to, that's not a bracket. I'm going to leave here as an exercise. Find the inverse for the multiplicative formal group. Okay, find what is supposed to be the inverse there. Using that definition, you should be able to figure it out. Okay, so we have multiplication by M maps, and then there might be other homs that we're interested in. But let me give a property of this multiplication by M maps. So let F be a formal group over a ring R. Then first, the multiplication by M map, it actually looks like M times T plus higher order terms. Okay, so the first term is M times T plus terms in T squared and higher. We will abbreviate this by hot. All right. And then, and B, more importantly, if M is a unit in R, then multiplication by M is actually an isomorphism of formal groups. Okay. By the way, as an example here, if our ring is the p-adics, okay, so if R here is the p-adic integers, then the units is just anything that is not in PZP. Okay, so so ZP minus PZP is all the units. So everything that is non-zero mod P. So this is p-adic integers such that U is non-zero mod P. All those are units. So if you have, for example, in Z5, if you're looking at in the 5 adics, multiplication by 3 is an isomorphism of the formal group. Okay, so how do you prove this? For A, you can just do it by induction. So for m bigger or equal to 0, you can use induction using the fact that f of xy is just x plus y plus ... So definitely f of x plus x, which would be multiplication by 2, that's 2x. And then if you keep going with in the induction, then you can easily show that this is the case for any multiplication by m map. And for m less than 0, you can use the fact that so f of t and it, so t and it, because I is the inverse, that gives you 0. This is t plus it plus ... and therefore I of t must start with minus t plus, and so on. Okay, so that tells you that the map, which is multiplication by -1, it starts with minus t, and the multiplication by -2 will start with -2, and so on, again using an induction, but now in the negative integer direction. How about a proof of B? So a proof of B, I'm not going to prove it in full, but you use the following lemma. It turns out, this is just a property of power series, nothing about formal groups, that if you have a unit, and f in RT, and f a power series such that f of t starts a t plus higher order terms, then there is a unique power series G such that f of g of t equals t, and g of f of t is t also. Okay, so there is a unique G that works, and this you can actually find also. I think the proof of this is also in the book. But just assuming that, if you use this, let's what people say, use it as a black box. Okay, just this is something about power series, and I'm not going to prove it. But if you assume that, then that's just saying that, so since m is a unit, I should actually not use star here, but actually cross for unit. No, it's not just non-zero. I really want units. So if m is a unit, then we are in business and m of t, we know from the first part that is mt plus higher order, then there is a unique map G that will do this, right? There's a unique G of t such that, so I'm going to call this, let me call these power series f of t. Okay. Then by the lemma, there is a unique G of t such that f of G of t equals G of f of t equals t. So there is a power series that works. But remember, in the definition, let me go back to the definition of Hom. There's got to be, for to be an isomorphism, it's not just, this is not the only property that you need. You also need both to be Hom. So I need this G to be a Hom. So I also need the G to have this property here. Okay, so let me show you that thus constructed, as long as G is the inverse power series of F, then G is also a Hom. So I actually need to show, so I need, what is it that I need? I need that to show that G of f of xy for my formal group, that is f of G of x, G of y, right? I need that. So let me show that part. So here it goes. So first, f, which is multiplication by m, but f, little f, is a Hom. So f is Hom. I don't want to cramp it here, so let me just write it here. So f of t, which is mt, is a Hom. That tells me that f of capital F is capital F of the little f's, right? And then what I'm going to do is, that is for any x and y, so I can apply it to little g of x and little g of y. Okay, so take x to be really g of x and y to be, that doesn't sound good. Let me just say that I can just evaluate anywhere I want, and this is going to be true for any x and y. So I can write the same equation, but for g, for little g. Right? And now I know that the property of this g that was given by the lemma is that f of g of x is actually the identity, right? This is the identity, and this is the identity. So I can, so this tells me that f of g of x, g of y equals f of x, oops, y. Okay, and what is left? Now I'm going to apply g to both sides. So g of f of g of x, g of y, that is g of f x y. But again, g composed with f, no matter what power series, this is the identity. So this gives me f of g of x, g of y is g of f of xy. And that is what I wanted. This implies that G is a Hom. And therefore, since I have a home in one direction and home in the other direction that are inverses of each other, then multiplication by m is an isomorphism. Oops, it's an iso. Okay. Very good. Great.
Can I ask a quick question?
Yes, yes, you can.
What restrictions do we make on R? What kind of rings are?
Priori R is just any ring. I don't think I've even used that R is a commutative ring, but for safety, I think might just assume that R is a commutative ring with an identity. But I
So
don't
does R have an ordering on it?
An ordering?
Yeah. When we say that like m is greater than or equal to 0 or m is less than 0, initially I thought, oh, like R is basically the integers, but
Oh, well, R has a 1,
Mhm.
and m is just m times 1.
Okay.
So by m bigger or equal to 0, I really mean I'm an integer.
Mhm.
So the integers, you can think of the integers inside R, except that, it might be that the ring is of characteristic P itself, that is allowed, in which case, at some point, you're going to get into, when m is P, then I have, I get a 0, but you see, if I take m to be P, then P itself is not a unit. So it's not any longer an isomorphism. Right?
Mm-hmm.
If the characteristic of R is P, then the multiplication by P map will not be an isomorphism because it doesn't satisfy the property, the hypothesis of the theorem, of the proposition.
Okay. Awesome. Thank you.
But again, I keep thinking in the back of my mind, I keep thinking that R is the p-adic integers. The diffraction field of that is QP, and that I have also a maximal ideal, which is PZP. That's the example that I have all the time in my head when I'm doing all this, which is where we will apply all this. Okay. All right. So now what we're going to do is put a group attached to a formal group. So now we're going to do groups associated to formal groups. All right, so now we are going to think of R to be a complete local ring. A complete local ring with respect to the maximal ideal M in R. So it's local. There is only one maximal ideal, and then we're going to take little k to be the residue field. So this is R modulo M is called the residue field. And an F is going to be a formal group over R with law capital F of XY. Okay. Throughout, you can think of, again, R to be ZP, M to be PZP, then the residue field is ZP modulo PZP, which is isomorphic to Z mod PZ, or FP. Okay, and so we can attach if I have a formal group, now I can attach a group to it, the group associated to the formal group. Oops. Usually I'm not writing them like that, so let me just the group associated to the formal group, denoted by f of m, is the set M, which M has its own group structure. It has its own group structure that comes from the ring. M with respect to addition is a group. So we're going to change that addition and put another addition instead of that one with operation x plus y is going to be, now instead of just adding in the maximal ideal, I'm going to add using my capital F for any x and y in the maximal ideal, and the inverse. So the inverse, what is the additive inverse element? That's I of x for x also in the maximal ideal. Okay, so I put a new group structure on that maximal ideal, and that gives me new groups to work with. So remember, for example, we had the formal additive group. GA. So yeah, no page. So now what is GA hat of M? It is just going to be M plus. Okay, in that case, addition is just addition on the formal group, is just addition on the maximal ideal. So you just get M plus. And note this this group, the group associated to the formal group, fits in a sequence, in an exact sequence as follows. It fits in this group. It fits inside the ring R, and if you do the quotient of the two, then you get the residue field, right? Okay. So what about the multiplicative group? So the formal multiplicative group GM, now when I add points to it, then that is actually for every, as I said, 1 plus an element in the maximal ideal, those are units. So the group that you actually get is 1 plus m, or is isomorphic rather to 1 plus m under multiplication. Okay, so those are units under multiplication. And in here, we also note that it fits in a sequence. It fits in the following sequence. So if I have R, and the units fit in there, and when I do the quotient of the two, what I get is the non-zero elements of the residue field. Okay, so these are the units that are 1 modulo the maximal ideal. Okay, so here, if you take in the example of that R is ZP, what this is saying is that ZP pros, which are elements that are non-zero modulo P, I have the units that are 1 modulo PZP. Those are units. And when I do the quotient, what do I get? I have everything except that I have the quotient of the two are classes of units. The classes that are not 1 are the classes that are 1, 2, 3, 4, 5, and so on, modulo P, non-zero modulo P. So there is 1 class in the quotient for every element of ZP modulo PZP, which is the residue field. So it fits in there. Okay, so now we come to our hero here, which is what about if you have an elliptic curve over R, then we've built the formal group, and we have the formal group attached to M. So that is just the maximal ideal with the maximal ideal with the addition of z values that comes from the elliptic curve. Recall that we showed that M actually embeds in here, where K is the fraction field of R, right? So so we do have that. So what this is actually saying is that in terms of the formal group, then there is a homomorphism like that that goes in there. Okay, but it turns out that this is no longer, I would love to say that there is an exact sequence like in the ones we've seen before. Sort of like this, where this is the elliptic curve. If this is elliptic curve over K, this is the same elliptic curve, but considered over the finite field or the residue field. But there is a problem here. There are 2 problems. First, this may not be an elliptic curve. It may not be smooth. And second, is this injective? Is it exact? So it turns out that often we will have this. Okay, so often we will have this exact sequence here, but not always. And we will later, we will identify when this actually happens, that we have this decomposition. But notice that this is what I was talking about last time, which is that if K is QP, for example, capital K is QP, then I want to know what are the points on the elliptic curve for QP. And this is telling me that there is a big chunk, which is the formal group, and a little chunk, because now an elliptic curve over a finite field, we know by Haas's bound, this is just a finite number of points, and we can actually just compute by hand what is the right-hand side of this formal, of this exact sequence. So it's telling me that it's just almost everything comes from the formal group when I think about the elliptic curve over the p-adics. So if I am able to settle this exact sequence, then I know a lot of information about elliptic curves over the p-adics. By the way, also, why do I care about the p-adics? Well, Q itself, which I really care about, elliptic curves over Q, Q is inside the p-adics for any p, right? Because the p-adix is a completion of Q. So Q is in there, which tells me that if you fix one of these embeddings, then the points over Q are inside the points over the p-adix. So any information I can get about elliptic curves over the p-adix carries down to elliptic curves over Q because of that inclusion. And what we're going to do, for example, is find some bounds on what kind of torsion points, for example, you can have over the p-adix, and that is going to tell me something about the bound on, well, what kind of torsion points you have over Q. For example, we're going to use this later on to prove that in most cases, if you have an elliptic curve over Q with integer coefficients, the torsion points are defined over the integers. There's no rational solutions that are torsion points, except we'll see that actually the prime 2 ruins that a little bit, and you can have a 2 in the denominator of a torsion point, and that's it. Okay, but we're going to use this approach of p-adic approach to prove that kind of thing. All right, so I'm going to stop here, and then I'm going to prove some properties about groups over the groups associated to formal groups, but I'll just want to take a tiny break. I'll be right back.